I'm Tyrell Bass, and in this video, I'll be introducing some of the concepts used in our research towards bridging quantum mechanical accuracy and the scalability of classical simulations. Let's say I have a gold bar, and I want to pull it apart until it breaks. On the right, we see the stress-strain curve. As we increase the strain on the material, stress increases up until a critical point where the material breaks, relieving that stress. But where does the break begin? We can zoom in to the atomic structure of the gold bar, and we can see it begin with the breaking of the bonds between atoms. Here we have a lattice of gold atoms. Again, we're going to pull it apart to increase strain, and once we've reached this critical breaking point, the atomic bonds begin to fail and the lattice separates. To study effects like this at the atomic scale, we use molecular dynamics. Molecular dynamics is a simulation technique where we can model how atoms and molecules move and interact over time by solving Newton's equations of motion. We can find our force through the potential energy, so if we know mass and potential energy, we can find out how these atoms move. The way in which we define our potential energy determines how our system will move. In a simpler case, we look at two atoms interacting through a pair potential. This pair potential function is dependent only on the distance between the two atoms. At equilibrium distance, the slope is 0, and they're at rest. If they get too close together, they will repel, and when they get too far apart, they begin to attract each other. And at infinite distance, this force will vanish. Pair potentials describe gases and liquids well, but not ordered crystals. So for a metal like gold, we'll need to use a different model. The embedded atom method is standard for metals. We have our usual pair interactions acting on the atoms, but we also must consider their electronic structure. The embedded atom method considers a symmetrical cloud or density of electrons, and the additional term it defines is the work required to embed this electron density into the host of other electron clouds. But what if our electron clouds aren't symmetrical? We'll need a different method to describe anisotropic effects in our material. The machine learning potentials allow us to describe asymmetrical effects by encoding angular dependence in descriptor functions. To recap, if we start with a pair potential, we can define a lattice as when each of these atoms lies at its equilibrium distance from one another. The embedded atom method adds in a correction for a symmetric electron cloud, which changes this equilibrium distance. The machine learning potentials allow us to encode angular dependence, meaning we can describe asymmetrical electron clouds, which again changes the equilibrium distance. In this comparison, we can see different behavior based on the potential used, with the machine learning potential being the most accurate of these three. The bulk of the research was doing simulations using these different methods. Here are some actual simulations of bulk gold visualized. This is bulk gold stretched along the y-axis. You can see atoms vibrating with thermal fluctuations while the lattice contracts along the other axes. At these scales, we don't see fracture, but we do capture an elastic response. So how do we know that what we're looking at now is a crystalline structure? We use the radial distribution function to quantify this. Here we have a unit cell of gold. It is a face-centered cubic crystal, meaning we'll find an atom at each corner and also on the center of each face of the cube. Say we're interested in this larger crystal. If we're looking at a structure built of these cells, we expect a particular shape on our radial distribution function graph. The radial distribution function works by taking a reference atom and counting each of its nearest neighbors to show a representative probability of finding an atom at that distance. We can think of this like a bar graph where each bar corresponds to a distance an atom was found from that reference atom. In an ideal case, our graph would look like bars like this, but because of thermal fluctuations, we should see something more like this line. But what if we aren't looking at a crystal structure? In a liquid, atoms are disordered. If we take a reference atom and measure distances, we'll have a more diverse group of distances, no longer seeing sharp peaks, but broad peaks with a continuous distribution. We've shown that macroscopic effects can be described from the movement of their atoms using molecular dynamics. Our molecular dynamics models vary with the definition of the potential energy. We use machine learning potentials to simulate our gold system and benchmark it against the industry standard embedded atom method potentials. This brings us closer to quantum accuracy in large-scale molecular dynamics simulations. While this work was focused on gold, molecular dynamics is used for all types of applications. Quantum accurate simulations at scale can speed up the discovery of new medicines. It can help discover stronger and lighter alloys, and it can drive breakthroughs in clean energy technologies like batteries or catalysts.